Hi, my name is Govinesh Sharma. My train number is 303520. So today our group will be presenting a well-known problem in the field of computer science and operation research, which is the traveling salesman problem, as known as a TSP. So we move on to the problem definition given by the TSP. So the problem definition given is given a list of cities and distance between each pair. Find the shortest possible route that visits each city exactly once and returns to the origin city. So the cities that are A, B, C, D, E. So we can see that cities from A to B, the possible route is 12. So we can go for the next. So in our case study, we will demonstrate how the traveling assessment problem can be solved using the two different algorithm design strategies, which is brute force, the simplest and the most straightforward method, and the dynamic programming, which is the more optimized approach that save the time using memory. So first, I will be present about the brute force, the executive search. So this is the all possible routes and their distance. There are 24 possible routes. So we go for the first one. First one is from B to C, D, E, A means the total is 21. So we can see that B, C 3, C, D 6, to D to E is 4, and E to A is 8. So when we total is 21. Same goes to the other 24 possible routes. So the second one is B, C, E, D, A, and the possible routes is 46 kilometer. And third is B, D, C, E, A is 41. Fourth is B, D, C, E, A, 41 also. And fifth is B, E, C, D, A is 47. And 6 is BEDCA is 22 kilometer. 7 is CBDEA is 22, and the 8th possible route is CBEDA is total is 28 kilometer. And the number 9 is CDEBEA is 23. 10 is CDBA is 24. 11 is CEBDA is 48. 12 is CEDBA is 43, and next is DBCEA is 38. 14 is DBECA is 39. 15 is DCBEA is 19, and 16 is DCEBA is 40. So the last 8 is 17 is DCBACA is 19. 18 is DECBA to 29 kilometer. 19 is EBCDA is 30. 20 is EBDCA is 25. 21 is ECBDA is 49. 22 is ECDBA is 45. And the last second is EDCBA is 24. And the last one is EDCBA is 25 kilometer. So the shortest route from these 24 possible routes is the two shortest route, which is DCBEA with a total distance is 19 kilometer. So the second is DEBCA is total kilometer is 19 kilometer. So next, my groupmate will continue the presentation. Thank you.
Hello, my name is Sufakisha and my magic number is 307946, and today I am going to explain on algorithm analysis for brute force TSP solution. First of all is algorithm overview. The brute force approach solves the traveling salesman problem TSP by generating all possible routes, the permutation of cities, calculating the total distance for each route, and then selecting the shortest route. For the given 5-city problem, this evaluates 24 possible routes since the starting city is fixed. Next is time complexity analysis. Theoretical complexity, which is O n factorial. For n cities, there are n minus 1 factorial permutations since we fixed the starting city. Each permutation requires n minus 1 distance calculation for n minus 1 edges between cities. When applied to the 5-city problem, permutations is 5 minus 1 factorial, which is 24. Operations per permutation is 4 distance calculations. Total operations is 24 times 4, which is 96 computations. Next is growth rate comparison. For 5 cities, permutation is 24 and the total operation is 96, which is explained before. If 10 cities, the permutation is 362,880 and the total operations is around 3.6 million. For 15 cities, the permutations becomes 87 billion and the total operations is around 1.2 trillion. The factorial growth makes brute force impractical for n more than 10. At n equals to 15, it would require 1.2 trillion operations, which is 3 hours at 1 billion operations per second. At n20, it exceeds 800 years of computation. Next is space complexity analysis. Memory usage is O and stores the current permutation, which is ON space. The best route found so far, ON. The distance matrix, ON square, but input size is fixed. For the 5 city problem, it uses very minimal memory usage, which is almost negligible for modern computers. Next is correctness and optimality. Brute force evaluates every possible route, so it cannot miss the shortest path. 2 optimal routes are identified, which is A, D, C, B, E to A, which is 19 kilometers, and the second one is A, D, E, B, C to A, which is also 19 kilometers. Symmetry in distances. Both routes uses the same edges but in reverse order. Next is efficient local clusters. First one is DCBE, which is 11 kilometers, and then the second one is DEBC, which is 9 kilometers. Both are balanced by the long A to D, 19 kilometers, and the short return legs E to A or C to A. Next is practical limitations. When brute force works, it works when small problems n is equals or smaller than 10. Computationally feasible 5-city TSP can be solved in microseconds. When to avoid brute force? When n is more than 10 and the factorial growth becomes prohibitive.
Okay, Assalamualaikum warahmatullahi wabarakatuh. So my name is Muhammad Ali Farhan. So I present about the algorithm overview, which is HELCAP. The HELCAP algorithm solves the traveling salesman's problem using dynamic programming. It's powerful because it takes advantage of 2 key ideas, which is first is overlapping subproblems, which is the same smaller roads are reused in different parts instead of recalculating them. The algorithm save and reuse the results. And then for the second one, second is optimal substructure, which is the best overall part includes the best solution to smaller parts. So we can build the full solution step by step from smaller optimal ones. HELCAPs use a bitmask to track visited cities and gradually build the solution from small sets to the full tour, making it much more efficient than brute force. Why use dynamic programming? Okay, first of all is dynamic programming works well here because the ISP has overlapping subproblems and optimal substructure. For example, smaller roads like A to B to C are reused in many larger tours. So instead of recalculating them, we reuse the results. Also, the best route through cities A, B, and C must include the best path from A to B to C because there is the optimal substructure. The HELCAP algorithm uses a bitmask to track visited cities and store the minimum cost to reach each city after visiting certain subsets. It built the solution step by step, starting from smaller subsets and growing toward the full tour. Demonstrate HELCAP with dynamic programming table. To understand how the HELCAP algorithm works, let's look at how it uses a dynamic programming table, which is DPSJ. Here S is the set of visited cities, represented using a bit mass. J is the current city we were ending at. The value dp as sj stores the minimum cost to reach city j from the starting city a, having already visited all cities in set s. So let's look at few examples, which is a b ending at b. So we have a to b equal to 12, and then ac ending to c, a to c equal to 10, abc and ending at c, a, b, c. So 12 plus 3 equal to 15. So A, B, C, which is ending at B, A, C, B. So the total value, which is 10 plus 3. So we have 13. So A, B, D ending at D. So A, B, D, so 12 plus 7, so equal to 19. The algorithm continues building larger subsets by adding the city at a time and choosing the cheapest way to reach each one. Finally, when all cities are visited, we compute the total tour cost by adding the cost to return to city A. That's it, dp all cities j plus distance from j to A. In this example, so the shortest path is ADC BEA with a total cost of 19.
So for time complexity analysis, the theoretical complexity is O, which open bracket n square multiplied by 2 to the power of n. So for n cities, there are 2 power of n subsets of cities excluding the start city. And for each subset, we consider n possible current cities, which is total n multiplied by 2 power of n. And for each state dp si, we iterate over j over s, another n factor. So for this, we applied to the 5 city problem. So the subsets is 2 power of 5, which equals to 32, and the cities are 5, and the total operations is approximately 5 multiplied by 2 to the power of 5, which equals to 160 computations. And this is more than brute force 96 operations, but is still feasible. For the growth rate, for cities n, for cities n5, the subsets will be 32, and total dp states will be 160. For cities n10, we have 32,768 subsets and 10,240 total dp states. For 15 cities, we have 87 billion subsets and approximately 4,091 and 532 total dp states. And lastly, for 20 cities, we could have approximately 1 million subsets and 20 million total dp states. So the growth is exponential but much slower than factorial. And at n20, the method is still practical, unlike brute force. For space complexity analysis, the dp table is O n multiplied by 2 the power of n. So the distance matrix would be O n square multiplied by the input. So total would be O n multiplied by 2 power of n. And for n5, the dp has 5 multiplied by 2 the power of 5, which is 32, which equals to 160 entries. So it is very small in memory. So this method requires more memory than brute force, but still efficient for small and medium size n. So for correctness and optimality, HELCUP is very exact, which means it guarantees the shortest path. So like brute force, it explores all routes, but in a smart, reusable way. So for the result for the 5 cities, same optimal solution is found. So the first solution is A, from city A to D, C, B, E, A, which equals to 19 kilometers. And the second route is A, D, E, B, C, A, which is also 19 kilometers. So the practical limitations for dynamic programming of HELCUP, So when does haircut works? It works when the value of n is less than 20 or equals to 20, and it solves exactly in reasonable time, and it is suitable for planning, scheduling small logistics. So when to avoid dynamic programming or haircut is when the n number is more than 25. Memory and time demand will grow steeply, and when the real world problems with n equals to 50 plus will need heuristics.
Next up is technique comparison between brute force and dynamic programming. For brute force, the time complexity is O n factorial and the practical use is n equals or smaller than 10 and the optimality guarantee is yes. For dynamic programming, time complexity is O n square 2 power of n. Practical use is when n is equals or less than 20 and the optimality guarantee is yes. Brute force guarantees accuracy by exhaustively checking all possible routes, making it ideal for very small inputs. However, it quickly becomes infeasible due to its factorial time complexity, especially when the number of cities exceeds 10. In contrast, dynamic programming, which is held-cup algorithm, offers a more scalable alternative by reusing sub-problem results. Although it still has exponential growth, it performs significantly better than brute force and can handle up to 20 cities efficiently. While both are exact methods, the trade-off lies in choosing brute force for simplicity and small inputs versus dynamic programming for better performance on medium-sized problems. That's all from me. Next, my friend will continue. Thank you.